And we will be video recording each session. I'm using this OBS Studio software to do that. So on the course's pilot page, let me go to that. Let me see. So on the course's pilot page, and I sent you a note, I sent you an email with a couple links, and I also have those links up right here. So we will be using Pilot for our class meetings. We will meet every Monday and Wednesday, 6:30 to 8:45 in Collaborate Ultra, but that's all we'll be using Pilot for. As far as content for the class goes, the notes will all be on my personal website. So that's this one here, daniel-slilotti.xyz. So I've got 2 classes this summer. Here's the link for Calc 3. And you'll notice that I have the lectures on the sections of the text already up. So these are the notes that I made while doing the video on YouTube, that you should have watched before coming here today. Did anybody not watch that? And everyone got the message you were supposed to watch it, right? Did anybody not watch that video yet? Okay, good. So all of those video lectures are up on my YouTube channel, and all the notes for those videos are here. So I mean, today you should have gone through the lecture for 2.1 and 2.2. Nothing really that unfamiliar to you should have happened there. Just introduction to three-dimensional coordinate systems. And what we're going to do now during these sessions is we are going to go through all of the exercises on the syllabus for the course. So here's the syllabus for the course. All right, so in each section we've got some list of sample homework problems. I will add to those, or maybe take away some stuff as we go on, to draw your attention, and get your practice for more types of problems. Also, I'm going to have to add section 2.6 into chapter 2. 2.6 is not on the syllabus, but we really do need to cover it. Okay, so for next time, you should go through the lecture on 2.3 and 2.4. Maybe we won't get through all the material on both of these sections, but do watch the videos on 2.3 and 2.4 for next time, and then go through the sample homework problems as much as you can, before we meet in person. Okay, so that's the syllabus for the course, and on the syllabus there's a link to the textbook, and the textbook is free open source textbook. Here it is. It's a good textbook. It's got it's got all the material, and it's presented very well. The only problem is there's typos in the exercises. So a lot of times the solution in the back of the book isn't right. Not a lot of the time, sometimes. And sometimes the problem itself is like messed up so that it can't be solved. And there's supposed to be something. And unfortunately, that's the state of the text at the moment. So I know a few of them, and I'll let you know about them ahead of time. when I can. So the syllabus got the link for the text. Actually, I should have put that link on the pilot page too. I'll do that. What next? Course policies. Oh yeah, here's again, here's my YouTube channel, and the if you go to playlists, the Math 2320 is in here somewhere. 2530, 23. Huh. Don't I have? No, I don't want to do that. It was? I didn't see it for some reason. Anyway, so here playlists. Here, this is a little easier. I hear it. No, that's 2310. 23. Where is it? That's Calc 2. Oh, here it is. Oh, I didn't call it 2320. It's called Calc 3. Okay, so the y squared. It's got all the video lectures on it there. Okay. Hi, everybody. This is our so you can go through those, as fast or as slow. I mean, not as slow, but I mean, as fast as you might like to go through them. But we definitely have to keep up the pace because there's a lot of material to cover this summer. What else did I want to mention? And then as far as grading for the course goes, we'll have 4 midterm exams and 1 final exam. 20% for each of those grades. Very simple. And the final score is the average of those items plugged into this grading scale here. 90 is an A, 75 is a B, 60 is a C, 45 is a D, and less than 45 is an F. Okay. So a real simple grading scheme. And the final exam is comprehensive. And if you look at the syllabus, you'll see, what the first 4 the midterms cover. The first exam, we're going to cover Chapter 2 and 3. Second exam, Chapter 4. Third, Chapter 5. And fourth exam, Chapter 6. So let's write that down. Exam 1 will cover Chapters 2 and 3. Exam 2 will cover Chapter 4. Exam 3 will cover Chapter 5. And Exam 4, Chapter 6. For the exams, we will meet here in Collaborate Ultra. Okay, you should have or must have a working webcam. Okay, so during the exam, you will turn on your webcam so I can, see, what's going on with everybody so we can have a proctored test environment. So during the exam, you will turn on your webcam. You will complete the exam on pencil and paper. And then you will scan the exam, your work, into one PDF file using, does everybody have a smartphone? Does anyone not have a smartphone? Does anyone not own a smartphone? Or if you don't, do you have a scanner? Okay, so what you need to do is, download, these are free apps. Adobe Scan or Cam Scanner is a nice one. Or other scanning software. So you'll scan your exam using your phone into one PDF file, and then you will upload the exam to Dropbox on Pilot. So on Pilot, page under the up here under the assessment tab, you see there's a Dropbox there, right? And there will be a folder there for each exam. There isn't one now, of course, but you can make one. So here will be the folder for exam 1. So you'll scan, you'll make a PDF file, and you'll upload it to that. So please use one of these smartphone apps. I know iOS has also some other particular apps that they use, but these smartphone apps, they're optimized for scanning just like simple documents, simple black and white documents. If you use a flatbed scanner, so some of you may still have those old flatbed scanners. If you do use that, what you need to do is set the resolution way down. Because if you don't, it'll make those are used for scanning pictures for photographs, right? So it'll make some super high resolution color scan or something like that. And the thing will turn out to be 100 megabytes or 50 megabytes or something like that. And it won't upload to Dropbox. It'll be too big, and it'll be too big for me to handle with my software for grading and all that stuff. So if you do use a flatbed scanner, make sure to set the resolution way down. Okay. So that's it for introductions. Any questions before we get started on the material for today? Also, please turn on your microphones and speak freely. Don't, don't use the hand raising thing and send chats, because it's difficult for me to skip back and forth between what I'm writing and the chat windows over here. And it's hard for other people to follow along with what you're saying, perhaps, and what I'm saying. So please turn on your microphones and just speak. Okay, it's not a big class. There's no need to rest on formalities here. Just if you have a question, just speak up. Okay, anybody got any questions? Anybody? We got 12 people here now, besides me.
Will these lectures be recorded?
Yeah, I'm recording the lecture now, and yeah, that's right. I should have mentioned that. I'm recording the lecture now, and I'll post those on YouTube as well.
Okay, sweet.
Yeah. Yeah, same question. Yes, yes. These will be recorded, and these notes that I'm writing, I'll put them up on the website as well. The Daniel-Slavati.xyz. Anything else? Alrighty. So, no, not 1.1, 2.1. So, starting off with, click below. Please go away. Do I need to update that? All right. So, as you can see, there's the on. Oh, another little warning about the book. There's the online book here. So if you go to this OpenStax Calc 3 book, there's view online, and then there's download a PDF. The online and the PDF are slightly different. So not that different, but there are a few differences here and there. So if you go with the view the online one, that's what I'll be doing. Okay. Sorry for that. I mean, these books are a huge undertaking, as you can imagine. It's hard to get everything like perfect, and it's a fairly new book. So subsequent versions are going to have those details ironed out, but it's not a big deal. I haven't had anyone have a problem really with the little snafus that are in there. Okay, so on the syllabus, let me pull the syllabus up. Section 2.1, 1, 2, 11, 16, 18, and we'll if you have some other problems maybe you'd like to see, we could do those too. So number 1, for the following exercises, consider the points P -1, 3, Q is 1, 5, R is -3, 7. Determine the requested vectors and express each of them, A, in component form, B, using the standard unit vectors. The standard unit vectors, those are the I, J, and K vectors. So for number 1, all right, we've got P is -1, 3, Q is 1, 5, and so this is the vector who PQ, head Q, tail P. So the vector PQ can be written in different forms. I like the component form myself. I feel it's more organized. Other people like the IJK form. But anyway, you'll notice this is a vector in 2 dimensions, right? So we have 2 components in the vector, head minus tail. So 1 minus -1 is 2. 5 minus 3 is 2. Right? So that's the component form, or you can write it in the unit vector, sum of unit vector forms, 2i plus 2j, where I is that vector 1, 0, and j is the vector 0, 1. Okay. Number 2. Number 2. PR, same thing. So minus 1, 3, minus 3, 7. All right, that's P, this is R. So the vector PR minus 3 minus 1 is minus 2. 7 minus 3 is 4, so that's minus 2I plus 4J. Okay, so, again, you can use whichever notation you like for vectors. Sometimes you use one, sometimes the other. Or sometimes you may want to just stick with one. I usually stick with the component forms. Number 11. Well, let's take a look at numbers 9 and 10, since we've already done 1 and 2. So number 9, it asks for the unit vector in the direction of PQ. So the unit vector in the direction of PQ, that's number 9. All right, the length of PQ is the square root of the components squared. So that's 2 squared plus 2 squared. So that's 2 square root 2, or square root of 8. Okay, so that's the length of PQ. So actually I don't have space to do this here. So number 9, it asks for the unit vector in the same direction as PQ. So in order to get that, you find the length itself of PQ, and now the vector PQ divided by the length of PQ is a unit vector in the same direction as PQ itself. So right here you have PQ, and the length is 2 square root 2, right? So that's what? That's 2 times 1.4, so 3.4 or something like that. So the unit vector, so this vector u in the same direction as PQ, is PQ divided by its length. Right, to compress it down to length 1, or stretch it to length 1. So that's going to be 1 over 2 root 2 times the vector 2, 2. So that's 1 over root 2, 1 over root 2. Okay, so that's a unit vector in the direction of PQ. For the unit vector in the direction of PR, which is equal to minus 2, 4, first take the length of PR, and that's the square root of 2 squared plus 4 squared. So square root 20. So it's 2 square root 5. right? So the unit vector in this case, so you can write it in two different ways. Instead of writing it as PR over the length of PR, you can write it as 1 over the length of PR times PR. It's another way to write it. Right, so that's 1 over 2 root 5 times negative 2, 4. So that's equal to 1 over square root 5, 2 over square root, or negative 1 over square root 5, and 2 over square root 5. Okay, so that's an important concept, this notion of a unit vector in a given direction of another vector. So that gets a lot of play throughout the course. Number 11. A vector v has initial point, tail, negative 1, negative 3, and terminal point 2, 1. That's the head. Same question. Find the unit vector in the direction of v, and put the answer in component form. So that's just the same thing that we just did. So we've got minus 1, minus 3, and 2, 1. All right, so v, this is the vector v. So v is equal to 2 plus 1 is 3, head minus tail, and then 1 plus 3 is 4. So the unit vector in the same direction, right? What's the length of this vector? Does anyone recognize it? It's a special one.
Is it 5?
5, right, exactly. It's 1/5 times 3/4, so that's 3/5, 4/5. All right. Numbers 16 and 18. For the following exercises, use the given vectors a and b and determine their sum, their difference, and verify that a plus b satisfy the triangle inequality, and determine these vectors 2a minus b and 2a minus b in standard and component forms. So for 16, we've got vector a is 2i. So 2i would be that, 2 comma 0. And vector b is minus 2i plus 2j. It's 16, yeah. Minus 2i plus 2j. So minus 2, 2, like that. By the way, notice that in the text, vectors are written as these bold-faced letters. Of course, when you're doing handwriting, you can't really do that too easily. Excuse me. You can't do that too easily. So for handwriting, you use the this arrowhead notation above the letter, which represents the vector. So we need to find out what is a plus b and a minus b. So a plus b is 2, 0 plus minus 2, 2. So you just add the components and you get 0, 2. a minus b to 0 minus 2, 2. All right, so that's 2 minus 2 and 0 minus 2. So that's 4, negative 2. Verify that they satisfy the triangle inequality. The triangle inequality, I think I did not cover that. So if this is vector u and this is vector v, then, or vector a, and this is vector b, then this vector, well, then you can put another, yikes, copy of a over here, another copy of b right there, and then a plus b is that right there. So this is vector A, and that's vector A. This is vector B, and that's vector B. And then the vector A plus B is right here. Okay, and the triangle inequality says, well, the sum of the lengths of two sides of the triangle is more than the length of the third side. All right, so the triangle inequality says Alright, the length of A plus the length of B is greater than or equal to the length of A plus B. So here, the length of A is 2. The length of B is 2 root 2. Right, the square root of 2 squared plus 2 squared. And the length of A plus B, which is right here, is 2 again, right? So two plus 2 square root of 2 is bigger than or equal to 2. Okay, and then the the A minus B business, if we take this picture again, so you just take A and B drawn with the same, from the same tail endpoint. What's this vector here? What's that vector that stretches from here to here? Well, A plus whatever this is, A plus question mark should be equal to B. So what's question mark going to be? In terms of A and B. Just solve it.
Is it B minus A?
B minus A. Right. Vector addition, you take the vectors and put them tip to tail. Here's A, or head to tail. Here's A, and here's the head of A, and put the tail of B minus A there, and then add them together. A plus B minus A is B. Right. So just like this picture up here. So what's the triangle inequality here telling us? Well, okay, it says the triangle inequality, it says several things, but says that the sum of the lengths of any two sides of the triangle is bigger than or equal to the sum of the third side, or the length of the third side. So the triangle inequality says here A plus, well, the length of B minus A should be bigger than or equal to the length of B. Right? And it also says that the length of B minus A, right, this also means the length of B minus A is bigger than or equal to the length of B minus the length of A. Right, which is kind of neat how that works. Right, the length of B minus A is greater than the length of B minus the length of A. So that's a sort of alternative version of the triangle inequality. So here again, we've got the length of A was 2. The length of B was 2 root 2. And the length of B minus A is equal to what? Where was B minus A? B minus A, or this is A minus B, I'm sorry. I did this the wrong way. Oh, that's okay. This is A minus B. So what's B minus A? Right, this is A minus B. So what's B minus A?
Just -4 and 2?
Yeah, -4, 2. So it's the length of -4, 2. So that length is 16 plus 4, so square root 20. So 2 square root 5. So 2 square root 5 is bigger than the length of B minus 2, right? Because 2 square root 5 is bigger than 2 times square root 2 minus 1 if you factor out the 2, and these guys cancel. And root 5 is bigger than root 2 minus 1, right? Root 5 is like 2 point something, right? Square root of 5, 2.2 something. And square root 2 is 1.4, so 1.4 minus 1 is like 0.4. Right, so I forget what the square root of 5 is. Let me get my calculator out. So 2.23. And square root of 2 minus 1, 0.414. Right. So that's kind of neat. So square root of B minus A is bigger than the length of B minus A is bigger than the length of B minus the length of A. Or you can turn it the other way around. The length of A minus B is bigger than the length of A minus the length of B. There was one more bit with 16. 2A minus B. All right, so what was A? So the last bit of number 16, 2A minus B. So that's 2 times 2, 0, minus 2, 2. All right, so this is equal to 4, 0. And then I can distribute the minus sign through, and then just make an addition. So this is 6 minus 2. All right, so
I have a quick question.
Sure, yeah.
Are these just interchangeable, or are there situations where one's more convenient to use than the other? Like in terms of the subtraction and what we went over earlier with the addition.
Which one over the other? I'm sorry, the A minus B or the B minus A? Whoa.
Just with the inequality, I think we solved it slightly differently earlier, didn't we? It was or am I remembering something wrong? Yeah, it was the absolute of A plus absolute of B is greater than or equal to like.
Yeah, that's this one here. Yeah, that's the basic triangle inequality right there.
Okay.
Length of A plus the length of B is greater than or equal to the length of A plus B. Actually, if I erase this, you can see it better. All right, here's A plus B, drawn head to tail, and that's the basic triangle inequality right there.
Oh, so it's all just interchangeable. So it's not like a situation where one would be more convenient than the other to use. It's all just the same triangle inequality.
It's the same thing. This is the basic form. It's just that it just happens to work out this way. So here again, we've got a triangle. Triangle inequality is the length of two sides. The sum of the length of two sides is less than the length of the third. So which two sides? Well, something interesting happens. I'm going to take this side plus this side. All right, so the length of A plus the length of B minus A is going to be bigger than or equal to the length of the third side, which is B. So that's the basic triangle inequality. But then something interesting happens is now you can subtract the A from here and you get that. So alternate form. Of the triangle inequality for subtracting vectors. And that's what that is. But it just comes from the basic triangle inequality. See what I'm saying?
Yeah, thank you.
Yeah. I mean, here the triangle inequality, it also says like something like this. Just the length of two sides is greater than or equal to the length of the third side, the sum of the length of two sides. So, which two sides do we pick? Well, it looks neater if you pick side A and side B and you add those, because this is, length A plus length B, and this is length A plus B. So it kind of has some meaning here. Here, it doesn't really have as much sort of meaning algebraically. But you can put whichever two sides on the left that you want. But sometimes the two sides that you pick are give you something interesting, like this here. When would you get equality in the triangle inequality? When would you get equality? Right, in both of these problems here, the triangle inequality was strict inequality, right? 2 plus square root of 2 is a lot bigger than 2. When would you actually get that the length of A plus the length of B equals the length of A plus B? When would that happen? Well, when you actually don't have a triangle. When A and B are what?
When A and B are collinear.
Collinear, in the same direction. Yep, exactly. When they're parallel, collinear, in the same direction, then you actually get equality in the triangle inequality. As long as you've got an actual triangle, then you'll have strict inequality. All right. 16, 18. Let A be a standard position vector with terminal at 0.25. Standard position, so they say terminal. I like the word head better. Standard position vector with terminal point at 2,5. That means so the head is at 2,5 and the tail's at 0, 0. And then let B be a vector with tail -1, 3 and head 1, 0. Find the magnitude of this thing here. All right, so we've got 0, 0 and 2, 5. So that is the vector A, and its coordinates are 2, 5. Right, head minus tail. The other vector is B, -1, 3 is the tail, and then the head is at 1, 0. So vector B, head minus tail, is 2, and then 0 minus 3, -3. Okay, and then they're asking about vector A minus 3B plus 14I, remember I is the vector 1, 0, minus 14J. Okay, so this is equal to 2, 5 minus 3B 2 minus 3 plus 14I, so that's 14, 0, minus 14J, 0 minus 14, well, minus like that. So what is this vector? This vector has x coordinate 2 minus 6, that's minus 4, plus 14 is 10, minus 0. So I've got a 10 here. And then 5 plus 9 is 14, minus 14, so we've got 0. So the length of A minus 3B plus 14I minus 14J is equal to the length of that, which is just 10. All right, that's what the question is asking. Number 25. By the way, like, you know, what should you be doing to study for the exam? So I'm doing these discussion problems in the book. Right, you should do them as well. Perhaps, you know, you're doing them and you do get stuck. What you should do is try doing them on your own. Like, hope, you know, preferably before class, but after class as well. And do them on your own and see if you can get the answers and then check your work against mine. If you're not getting the same answers or if you're getting something wrong, then you need to look into it and see you know, how you can fix it. And, you know, you could also do problems that are near the problems that are assigned. Like, they assign number 18 here. You know, like you might also do, say, number 17. And, of course, the odd-numbered problems have the answers for the odd-numbered problems are in the back here. All right, so there's an answer key for chapters 1, 2, 3, and so on and so forth. So you can look up answers to odd-numbered problems. You know, or if you get something wrong, you know, you can always do the problem again also. Okay, at this point in time in you know, at this stage in your learning process for this type of course, I mean, it's still just kind of doing drill. You know, the drills are much more sophisticated than they used to be when you were just factoring polynomials ad nauseum back in, you know, 10th grade or whatnot, 11th grade. You know, it's still doing drill. like, we'll have different concepts, and then you'll do problems that familiarize yourselves with the concept. And, that type of learning in mathematics is called cookbook learning. I give you a certain type of problem, and here's the recipe for solving it, and then you practice the recipe your own on these other problems. It's sort of a pejorative term. It's like a derogatory term, calling it cookbook learning, because it actually works, but people, it works for this level of mathematics. I mean, things can get, need to get more sophisticated later on if you are taking higher level math as a math major, or possibly as a computer science or engineering major, and it does, but a little bit of drill goes a long way. So that's your goal in practicing for the exams, is doing these problems, and getting them right, and doing some more problems if you need more help, need more practice, and if you need some help, just ask me. Say, Dr. Salati, can we, get some time to meet and work on some problems together? And, we can schedule some time. And you can, schedule some time with me, like after these class meetings, or we can do it over email. All right, I'm here to help, and, I want to help you. I want to help you succeed. So, just let me know if you need any extra help. For most of you, you should do well, I think, in the course. You wouldn't have gotten this far in your math career, if you weren't already, doing well. So typically students do better in Calc 3 than in Calc 2, for example. Okay, so 25. 25. For the following exercises, find vector v with the given magnitude and in the same direction as u. Okay, so these are nice problems. So we'll do 25 and 26. So we've got that the length of v is 7, and the direction of v is the same as direction of u well, they're calling it u, but they shouldn't call it u because it's not a unit vector. The 3, 4. So we've got this vector 3, 4, and what we want is a vector of length 7 that points in the same direction as 3, 4. So the first thing we need is you need a unit vector. So a unit vector. So what's a unit vector again? I'm sorry. It's remember? I don't think I said it explicitly. It's a vector whose length is
1, right?
1. Right, yeah. So a unit vector in the direction of, I guess we'll call it u because that's what they're calling it. Is 1 over the length of u times u itself. And the length of u, again, this is that special Pythagorean triple number here, 3, 4, 5. So this is 1/5, 3, 4. So that's 3/5, 4/5. So that's a unit vector. That's a vector of length 1 that points in the same direction as this guy here. So now if you want a vector of length 7 that goes in that direction, you just multiply it by 7. Is 7 times the unit vector for that direction. You have to start with the unit vector, because the unit vector has length 1, and when you multiply it by 7, the length gets multiplied by 7. So as long as that length is 1, when I multiply by 7, the length turns out to be 7. If this one had length 2, and then I multiply it by 7, then I'm going to have length 14. So you have to bring it down to length 7 or length 1 first, and then multiply it by the desired length. So that's 21 fifths, 28 fifths. Problem 26, same thing. A vector of length 3 in the direction of minus 2, 5.
I have a quick question.
Mm-hmm.
So with the final answer you circled, would you say that's equal to the value for vector v instead of just the length of it? That's just the value of vector v.
That's the value of vector v. The length of it is 7.
All right, I was just making sure.
Yeah, that is the vector v. A vector is always, something with multiple components, 2 components or 3 components, whatever dimension you're working in. And then the length of it is, so a vector has components, A, B, that's the vector, and then the length of that vector is the number, components, sum of the components squared, square root. So with this one, so then length 1 in this direction is 1 over the length of u times u. So the length of u is square root of 29, which is not a perfect square. So minus 2 over square root 29, 5 over square root 29. So that's the unit vector. And then length 3 in this direction. I guess I should call it v. And that answers your question a little better. So length 3 in this direction is v, which is equal to 3 times that. So minus 6 over square root 29, 15 over square root 29. All right. 29 for the following exercises, find the component form of u, where you're given the magnitude of the vector and the angle it makes with the positive x-axis. So in 29 and say in 30, we'll do both of those, I guess. Do we have another one in the syllabus like that? Let me see. 29 and 34. Well, 34 is the same thing. So we'll do that. So the length of u is 2, and the angle with the x-axis is 30 degrees. Alright, so the length of u is 2, and the angle is 30 degrees. So then find the components of u. Okay, well, the components of u are just the legs of the right triangle that defines this vector. Right? So this length is what? Right? It's 2, the length of the hypotenuse, times what? Since it's the length of the adjacent side of the angle.
Square root 3 over 2.
Right, cosine of 30. And this one is 2 sine 30. Right, so U is 2 cosine 30 degrees to sine 30 degrees. Cosine of 30 is is it 30 or is it? Oh, sorry. Square root 3 over 2. So it's just square root 3. How does it do that? And then sine of 30 is a half, so 2 times a half is just 1. Right, so given the length of a vector and some information about an angle like that, you can find the coordinates for the vector like so. And then 34, the length of U is 50, and the angle is 3 pi over 4, 3/4 pi. All right, 1/4 pi is 45 degrees. So here we got 3/4 pi. And the length of U is 50. Right? And this angle is right, so U has coordinates 50, right? The length of U. So even if it's not in the first quadrant, even if it's over here, the same stuff applies because the sine and cosine take into account the positive and negative, negating or not negating each coordinate based on what quadrant that you're in. So it's just 50 cosine 3 pi over 4, comma 50 sine 3 pi over 4. So that is minus 1 over root 2. And this is just 1 over root 2. Was it 50 or was it 5? Yeah, 50. Okay. Think of this for next time. So for next time, we'll go over this problem. Try this. Of course, if any of you are mechanical engineering students, then you're probably totally laughing at me now, like, how could he be going over this? It's so simple. But we got to get everyone up to speed. And we'll say this angle here is 40 degrees. Right, that angle is 40 degrees, meaning that this angle here is 140 degrees. But I'll leave that to you to figure out. 1. Find the components of V plus W, round to 2 decimal places. To find V plus W. 3, find the angle from the positive x-axis find the angle between v plus w and the positive x-axis. Where do you think that sum is going to be? Which quadrant do you think that sum is going to be in? V plus W. Will it be in quadrant 2 or quadrant 1, or will it point straight up?
I feel like it'll be in quadrant 1.
Yeah, it certainly looks like it's going to be in quadrant 1 because V is stronger than W. And, you know, its angle between the positive x-axis is less than the, and more of it is in the direction of the positive x-axis. W has got a smaller length than V, or magnitude than V, and less of that magnitude is in the direction of the negative x-axis. So in a tug of war along the x-axis, V would win, right? I mean, of course, the y component is going to be positive. Right? The y components of both of these vectors is positive, so when you add them, it's still going to be positive. But the x components, it looks like it's going to be positive, because along the x-axis, V is winning the tug of war. Okay, so give that a go for next time, and we'll go over the answer for that. What next? That was 34. 35. Vector u is given. Find the angle that vector u makes with the positive direction of the x-axis in the counterclockwise direction. So u is 5 root 2 minus 5 root 2. This is 35. Not an interesting one, unfortunately. Right, so the x coordinate is positive, the y coordinate is negative, and they're the same, right? X and y coordinates are the same, so here it is. Right, it makes a 45 degree in the fourth quadrant, because that's where the y coordinate is negative, x coordinate is positive, and you know it's got a 45 degree angle there. So you know this angle here is well, 360 minus 45, 315 degrees, which is 1, 2, 3, 4, 5, 6, 7. 7 pi over 4 radians. Unfortunately, that is not like a great example for this. Let me see if they've got another one where the angle isn't obvious. Well, 36. All right, we've got minus root 3 minus 1. Alright, so what quadrant is that vector in? Since x and y are both negative. What quadrant does that vector point in?
The third, right?
The third quadrant, right? Minus root 3 minus 1. Now, how does one find this angle here? If you look at this, if we look at this as for a vector in the first quadrant, it becomes a little clearer, the picture. So you've got this angle theta here with this vector, and then you've got coordinates A, B. Then, you've got this right triangle here, right, where this length along the bottom is A, and this length along the side there is B. Right, so tangent theta is opposite over adjacent, B over A, y coordinate over x coordinate. So theta is equal to arctangent, or an inverse tangent, of B over A. Right? And that works for, whether the vector is in the first quadrant, second quadrant, third or fourth quadrant. It works in any quadrant. Right, so here, what do we have? So, well, no, actually, it only works in the first two quadrants. Yeah, you have to measure the angle, right? Because arctangent gives you a number. Well, it gives you an angle from minus pi over 2 to pi over 2. Yeah. Yeah, unfortunately, it doesn't quite. Yeah, when theta is in quadrant 1 or 2. When you're in quadrant 3, you can do this same calculation and get the angle right there. Right, so this is like the negative of u, which is equal to positive square root 3 positive 1. Right, and then you can have this angle alpha right here. So alpha is the arctangent, right, of the y coordinate over the x coordinate. So that's 1 over root 3. Right, so alpha is arctangent 1 over root 3, which is equal to, well, it's again one of those special angles. I mean, it's better to, to not use these. I mean, it's a better example if you're not using these special angles. There's no real point in using them here. But, you can also write this as 1/2 over root 3 over 2. Right, and what angle does that? Right, the sine over cosine. The y coordinate is the sine, the x coordinate is the cosine. And so which angle is that? If this is 1/2 and this is root 3 over 2. Right, so the b is the sine and the a is the cosine. Right, the y coordinate, the thing on top, is the sine of that angle, and the a coordinate, the base of this triangle, that's the cosine, right? Sine over cosine. So this arctangent here is 30 degrees, right? So theta is what? 30 plus 180. Right? This trick with arctangent, it only works in quadrants 1 and 2. So if you're vector is not in quadrant 1 or 2. If you're in quadrant 3 or 4, what you can do is negate the vector, and that flips it through the origin. So here's u, here's the negative of u. Right? Find the angle for the negative, and then add 180 to that, right? Because this is a straight line. So it's 30 plus 180, so that's 210 degrees. Okay? Alrighty. 45. The speed of an object is the magnitude of its related velocity vector. Okay, so, if you've got an object that follows, that has a certain velocity, is thought of as a vector. It's something with a magnitude and a direction. And in the case of velocity, that magnitude is called speed. We will make the connection between velocity and speed much more explicit in chapter 3. Okay, but for now, speed is the magnitude of velocity. The speed of an object is the magnitude of its related velocity vector. A football is thrown by a quarterback, has an initial speed of 70 miles an hour and an angle of elevation of 30 degrees. Determine the velocity vector in miles per hour and express it in component form. Round to 2 decimal places. So this one's real simple here. You've got this 30 degrees above the horizontal, and the football is tossed in that direction, and of course the football is going to arc or whatnot. But as soon as it's released, that's the velocity vector. The velocity vector is 70 miles an hour. The angle there is 30. So what is the components of the velocity vector? Well, it's the length of v, cosine of 30, the length of v, sine of 30. Same as before. All right, you're using that right triangle that exists right here. All right, this is the angle 30. The adjacent side of the angle is given by the cosine, and the opposite side of the angle is given by the sine. Right, that whole SOHCAHTOA mnemonic, right? So v is equal to, if you've got the length of v times cosine of 30, length of v times sine of 30. And so this is 70 root 3 over 2, comma, 70 times a half. So that is 35 root 3, comma, 35. So that is the velocity vector of that football. Throughout Calculus 1 and Calculus 2, especially in Calc 1, you talk a lot about these distance, velocity, and acceleration type problems. The problem is in Calc 1 and 2 is that when you're talking about distance, velocity, and acceleration, motion is always along a straight line. Right? You're only going back and forth along a straight line. And, that's kind of like not a very useful situation. Here we're going to be talking about motion along any curve in 2 and 3 dimensions. So once you get to 3 dimensions, you have all the generality you need to describe the motion of a point through space. And we'll be able to talk about velocity, acceleration, and speed in really neat ways, and other things about the path of that point through space. So we'll do that in chapter 3. But this last problem in this section, 5.3, 2.1, number 53. So an airplane is flying in the direction of 43 degrees east of north, 43 degrees east of north, so I guess they mean like this, 43 degrees declining from north on the y-axis. At a speed of 550 miles an hour, the wind has speed 25 miles an hour, comes from the southeast of 15 degrees east of north. What are the ground speed and new direction of the airplane? So what they are saying is that if you add these two velocity vectors, the resulting vector is the the velocity of the plane relative to the ground. Okay, so in 53, so we assume that the sum of two plus the winds is the velocity relative to the ground. Airspeed plus wind speed is the ground speed. So here we've got this picture right there. So the airspeed is 550. So we need to draw a picture here. So here's the plane. So we'll call that vector P. So the length of P is 550 miles an hour, and the angle of declination here is 43 degrees. And the wind, what was it? It was 25 miles an hour. 25 miles an hour. And its angle of declination there was 15. So we need to know what the angles are. In order to use that sine and cosine business, you need to know what these angles are. So since this one is 43, this one is 45 plus 2 is 47 degrees. Right, they're supplementary angles or whatnot. They have to add up to 90. So that's 47. And this one here is 90 minus 15 is 75 degrees. So the plane's vector is 550 cosine of 47, comma 550 sine of 47, and the wind's vector is 25 cosine 75, 25 sine 75. So these are 381.57. Nope. Right, so we'll add these together. So if you've got some sort of calculations that need a bit of time to enter it into the calculator, has anyone ever used Wolfram Alpha? There's this website, Wolfram Alpha. It's an online version of Mathematica, and it's free. You can use that. So we're adding 550 cosine 47, 25 cosine 75. What was it? 47. Plus 25 cosine 75. So this is pretty nice. You can use this to do some nice. Oh, it is what I said. 381.569. Let's say 381.57. And for the y coordinate, it's the same thing, just with the signs. Or 26.39. Right, and then so that's the sum of those two vectors. So that gives you the velocity of the plane relative to the ground, but kind of the more interesting measure is going to be the actual speed. So the ground speed, the speed of the plane relative to the ground, is just going to be the length of this vector. So 381.57 squared plus 426.39 take the square root of that. All right, so you enter some stuff up here, and then Wolfram Alpha will tell you how it's interpreting the thing. It's interpreting it correctly. So 572.19 miles per hour. So ground speed is the length of that velocity vector, and that was 572.19 miles per hour. Right, so it was going 550 miles an hour, but then the wind the wind is kind of at its tail, so it gave it a little bit of a push. Right, it didn't get the whole 25 along with it, just like 22 and a bit from the 25 with it. All right, so that's 2.1 and 2.2. Similar problems, but we're going to be talking about three-dimensional space. Well, vectors and just coordinates in three-dimensional space in general. Actually, guys, why don't we take 5 minutes? Let's pause this. All right. Section 2.2. Number 61. So 2.2. So consider this box here. Find the coordinates of all these points on the box and the length of the diagonal of that box, right? So let's give that a quick draw. So also you need to practice your pictures. You really need to be able to draw effectively to really get the right perspective on things in this class. So you need to practice on that. It's not hard. I mean, once you have done it a few times. I mean, with things that are boxes like this, notice how they're being drawn. Lines on these boxes are always parallel to one or the other of the coordinate axes. Right? This line going this way is parallel to the y-axis. Going in the x direction, parallel to the x-axis. And in the z direction, parallel to the z-axis. So you have this box where these lines are all parallel to one or the other coordinate axes. All right, and this is the x-axis, this is the y-axis, and the one going up is the z-axis. And this point here is 2, 3, 5. 2, 3, 5. All right, and this point here is 0, 0, 0. So the x-coordinate there is 2. So this is 2, 0, 0. The y-coordinate is 3. Right, so this is 0, 3, 0. The z-coordinate is 5, 0, 5, 0. On the YZ plane, this is the YZ plane, we have the y and z. So that's 0, 3, 5. And on the xz coordinate plane, the x and the z, to, oops, what did I do? This is 0, 0, 5, excuse me. 0, 3, 0. And here, x and z, 2, 0, 5. And here, x and y, 2, 3, 0. And then this is 2, 3, 5. And then the diagonal of that box is right here. Right? The diagonal of that box is the vector v in standard position with tail at the origin and head at the point 2, 3, 5. That's vector 2, 3, 5. Right? And the length of v is, well, just like it is in 2 dimensions, it's 2 squared plus 3 squared plus 5 squared. So it's the square of the coordinates added together and then square root. Okay, so what do you get here? 4 plus 9 is 13 plus 25, so square root 38. Which 38 is 19 times 2, nothing to factor out there. Okay. So I'll talk more about drawing these points and surfaces and things like that, and you should be able to get the hang of it as we go along. But I mean, on the exams, I'm going to expect to see, some simple drawings out of you, because there are various sort of standard examples of surfaces that we go through quite a bit. And in order to really visualize what's going on, you need to be able to draw those surfaces. They don't have to be perfect, but, they have to be serviceable. All right, 63. For the following exercises, describe and graph the set of points that satisfy this given equation. So y minus 5, z minus 6 equals 0. Okay, what does this mean? This is equal to 0 when y is equal to 5 or z is equal to 6. Y equal to 5 Right, here's 5 on the y-axis. Right, maybe I'll put the 5 here. In 2 dimensions, when you say y equal to 5, it's all the 2-dimensional pairs x, y, where y is equal to 5. Here, this is all of the triples x, y, z of the form x for anything, y equal to 5, z equal to anything. So it's x, 5, z. So that turns out to be this plane here, which is parallel to the xz plane, right? This is the x-axis, z-axis, y-axis, and this is the plane y equals 5. So any point on this plane has coordinates x, 5, z. Right? So for any x and z that you want. Notice how I drew this plane. Right? It's parallel to the xz plane. So this line is parallel to the x-axis. This line is parallel to the z-axis. And then the plane z equal to 6. I'll put the z equal to 6 here, so it's not too out of place. No, it's not going to work there, is it? I guess we'll put it here. So that's the plane parallel to the xy plane. Containing all the points for any x coordinate, any y coordinate, and then z coordinate equal to 6. And that's parallel to the xy plane. So all the lines here that I'm going to draw, they're going to be parallel to either the x-axis or the y-axis. And, the intersection of these two planes is right there. It's a line. All right, so that's the surface being described by this equation, y minus 5 times z minus 6 equal to 0. All right, that equation is satisfied whenever y is equal to 5 or z is equal to 6. And all those points are right here on these two planes here. Okay? Now, of course, these planes extend infinitely in every direction, but, we can't really draw that, so, we just draw that much of it. 65. So y minus 1 squared plus z minus 1 squared equals 1. So describe the surface given by this equation. Y minus 1 squared plus z minus 1 squared equals 1. So y minus 1 squared plus z minus 1 squared equals 1. Now, in the yz plane, if we were just looking at the yz plane, what would that represent? What would this equation represent? If we were just looking at the YZ plane.
It would be a circle.
A circle centered at the point 1, 1, right? That is terrible. There we go. It's not much better. There we go. But we're not in the YZ plane. We're in XYZ space, right? So Y and Z are constrained like this, in this circle. But X can be anything. So what you get is that circle extended along the x-axis. So here's that circle, right? And then we take that circle in the YZ plane and you extend it. See if I can do it. you extend it in the direction of the x-axis. Because the x-coordinate can be anything. The y and z, the equation just has y and z. It's just y's and z's, that equation. All right? So the y and z are constrained as shown. But the x-coordinate can be anything. So what happens is you just take the picture in the yz plane and you extend it along the x-axis. No, it doesn't look good, does it? Maybe just that one. No, it still doesn't look right. So x-axis, y-axis, z-axis. Make sense? We do that kind of thing a lot. Okay, we get lots of surfaces by looking at equations of two variables in 3 dimensions. That's called a cylinder construction, because you're taking something and you're extending it into a cylinder. Yeah, I know that, you think of a cylinder as like a soda can type cylinder, but cylinder in a more general sense means when you take any two-dimensional construction and you extend it in the 3rd dimension. Right? So a similar example would be like this. So suppose we have y equals z squared, or let's say z equals y squared. Right? Z equals y squared looks like this, right? In the yz plane. In the yz plane, it's just this usual parabola, yeah? So in 3 dimensions, you just extend that parabola in the x direction. And that's called a cylinder construction. Get rid of those there, and then you just connect them up by lines parallel to the x-axis. See, like that? Parallel to the x-axis. Cylinder construction. So that's a circular cylinder. That's a parabolic cylinder, as you would call it. Okay, so that's the type of example that we do a lot of. And this is something you can draw. Right? I mean, we can all draw that parabola, and then we can draw a few copies of that parabola and then attach them with lines. So it's not as big a deal as you might think it would be at first glance. Alrighty. 67, 68. Oh. '67, '68, and '70, I think. So we'll talk about these in section 2.5. '67, '68, and '70. We'll talk about these in section 2.5. So it's more sort of general equations, equations of planes in 3 dimensions. So, I mean, we can talk about them now, but let's save the discussion of planes for later because we'll do it then. And there's no call for it doing it. There's no call for doing it early. 73. Find the equation of the sphere in standard form satisfies the given conditions. So you have a diameter PQ where P is this point, Q is that point. So how do you draw a sphere? Draw a circle. Draw another circle. Skewed sideways. Draw the equator. Okay, so draw a circle, draw a prime meridian, and then draw an equator like that. Okay, and then you get a serviceable picture of a sphere like that. Not hard, you know, right? I mean, of course, when you turn a sphere, a circle sideways, it becomes elliptical looking, right? It gets kind of a squashed thing when you when you look at it in perspective. If you're looking at it head on, it's circular. If you tilt it, it becomes more oval shaped. Okay, and that gives you a fairly nice picture of a sphere. So you've got a diameter of this sphere with the points minus 157, minus 157, and this point over here, minus 529. So the center of the sphere is the midpoint. Right there. Right, and you find the midpoint of a line segment in 3 dimensions, just like you do it in 2 dimensions. Its coordinates are the average of the coordinates. So the x-coordinate is the average of the x-coordinates. The y-coordinate is the average of the y-coordinates, so on and so forth. So here, this is minus 1 plus minus 5 over 2. 5 plus 2 over 2. And 9 plus 7 over 2. So the midpoint is minus 3, which is going to be the center of the sphere. Minus 3. 7 over 2 is 3.5. And 16 over 2 is 8. Okay, so I'll write it as 7 halves. All right, and the radius of the sphere is going to be what? One half the diameter. Right? How are we going to find that diameter? The length of that diameter. You guys all there? You're really silent.
Wouldn't it be the same way you find the magnitude of all the others? Just
Sure.
the square.
Yeah, you can think of this as this diameter as a vector, right? So it's 1/2 the length of. So think of this as the head and that as the tail. Minus 5 plus 1 minus 4. 2 minus 5 is minus 3, or you can think of it as the distance formula. 9 minus 7 is 2. All right, so 1/2 16 plus 9 plus 4, so square root 29 over 2. So that's the radius, square root 29 over 2. So the equation of the sphere with center HKL and radius R is, well, it's just the distance formula for three coordinates, x minus h squared plus y minus k squared plus z minus l squared is equal to the radius squared. Or you can put a square root over here equal to the radius. So in this case, you have x plus 3 squared, because the x coordinate is minus 3, plus y minus 7 halves squared, plus z minus 8 squared, z minus 8 squared, is the radius squared, going to be in this case 29 over 4. So that's the equation of that sphere. Okay, so it's just like, you know, a lot like analyzing circles in 2 dimensions, not too much different. All right, but the 2 takeaways from this problem here, if you want to find the midpoint of a line segment, it's just like in 3 dimensions, it's just like finding it in 2 dimensions. You take the x coordinates, add them, divide by 2, y coordinates, add them, divide by 2, z coordinates, add them, divide by 2. Okay, whereas it's just x and y in 2 dimensions. And then, you know, you also have the distance formula in 3 dimensions, right? So you could think of this as the length of a vector, or, you know, the square root of the difference in the coordinates squared. So 73, 76. So with 76, well, that was an example I did during the lecture. Find the center and radius of the sphere with this equation by transforming it into general form. So let's do 75 and give that one a try on your own. So 75, we have x squared plus y squared plus z squared minus 4z plus 3 equals 0. All right, so group the x's together and the y's together and the z's together and move the constant to the other side. Now complete the square. Well, x squared is a square, y squared is a square, z squared minus 4z, so z squared minus 4z, take the 4, divide by 2, and you get 2, and square it, and then add the 4 to both sides of the equation. All right, so we add 4 on the left and add 4 on the right. So then this gives us x squared plus y squared plus what's left here is a perfect square. It's z minus 2 squared equals 1. All right, so this is the sphere of radius 1, centered at x equal to 0, y equal to 0, z equal to 2. Sphere of radius 1 centered at 0, 0, 2. Eight. So these point now we're back to vectors. These problems are a lot like the ones in the last section. Although talk about angles and things like that in 3 dimensions is a little bit trickier, but you know, we will be able to understand that later in section 2.7. So let me see, 70, 78. We've got right P and Q, so just find the vector PQ. So we got 0, 10, 5. And you've got this point over here, Q, which is 1, 1, negative 3. So the vector PQ, again, is head minus tail. So 1 minus 0, 1 minus 10, minus 3, minus 5. So 1, negative 9, negative 8. And that's the component form. And then you also have the unit vector form. But instead of just I and j, now you've got this k vector, right, where I equals 1, 0, 0, j equals 0, 1, 0, and k is the unit vector 0, 0, 1. Okay, so we've got that same notion there. And then the arithmetic of vectors is the same as before. With 83, you've been given vectors A and B, and then you're just finding A plus B for A and minus 5A plus 3B. So we've got A equal to minus 1, minus 2, 4. B equal to minus 5, 6, minus 7. So A plus B is just add the components. Add component-wise. That's minus 6. Minus 2 plus 6 is 4. Minus 7 plus 4 is minus 3. And then for A, well, scalar multiplication works as before. Multiply each coordinate by 4. So it's minus 4, minus 8, 16. And then you can do these linear combinations of vectors, like how you would do in linear algebra. So minus 5a, that's 5, 10, minus 20. And 3b, that's minus 15, 18, minus 21. Adding together, you get minus 10, 28, minus 41. Okay, so, the algebra of vectors in 3 dimensions, just like into this coordinate algebra. Let's see what's left here. '85, '87, '92. That's 85. You can do that on your own. 87. Same. 92. So 85, 87, you can do those on your own. There's nothing big deal there. Just like what we did in 83 here. And then 92. So again, you've got this, notion of a unit vector. So you've got the vector 4 minus 3, 6. So a unit vector in the direction of A is, same as before, 1 over the length of A times A. So here the length of A is square root 16 plus 9 plus 36 times A itself, 4 minus 3, 6. So 16 plus 36 is 46, 52, 61. So it's just square root 61. And that's a prime number, I think. Okay, so same as before, you just take the length of A and you divide A by that length, or you multiply it by the reciprocal of that length, and that gives us a unit vector, right? A vector of length 1. (104), 111, and 113. 104, find a vector of magnitude 2 in the opposite direction than vector AB. So -1, -1, 1, and 0, 1, 1. So there's A and B. So the vector AB is head minus tail, 1, 2, 0. All right, so a vector of length 2 in the opposite direction. So the opposite direction means negative direction. Is as follows. Okay, well, what is the length of AB? Well, let me write it out. So take the length of AB, take its reciprocal, right? And when you multiply by that scalar, you're going to get a vector of length 1. But we don't want length 1, we want length 2. So put a 2 on top, right? Or a 3 if you want length 3. Oh, sorry, and you want to go in the opposite direction, so negate it. If you want to go in the same direction, leave it positive. Opposite just means negate it. All right, so this is minus 2 over the length of AB is square root 5 times this vector 1, 2, 0. So that is minus 2 over square root 5 minus 4 over square root 5, 0. So that's a vector of length 2 pointing in the opposite direction of AB. The negative direction, just, this way. 104, 111, let's see, in just the last couple minutes here. Oh, that was 104. 111 and 113. This is more and these we can leave them out. There's nothing here that is oh no, these aren't very good problems. So just 111 and 113, you can omit those. Okay. We're going to talk a lot more about force and work and all these a lot of nice physics applications in here. This by the way, this course, I mean, I hope you find it to be, but the mathematics that you're going to learn in this course, this is like some of the most beautiful stuff. It's probably the most beautiful mathematics that was developed in the 18th and 19th centuries. It's pretty old. I mean, hundreds of years old, 18th and 19th centuries, but it's definitely sort of like a crowning achievement of what people were able to do in those centuries. And it's very beautiful stuff and a lot of really nice physics applications. So we'll go over those as the semester progresses. Okay. So for next time, I'll send out emails, to remind you, and I'm going to post these notes online and the video, of course, on YouTube. Watch the lecture for 2.3 and 2.4, dot product, cross product. So watch the lecture for sections 2.3 and 2.4. And we'll see you Wednesday evening, okay? All right, everybody, have a good night. Have a good one. You too.
Dr. Salati,
Yes.